Hello, I am Hernández Rosas, and I want to welcome you to the presentation of my project, Electrospun polylactic acid, PLA, and polybutyrene adipat coterephthalate, PBAT, nanofibers for controlled curcumin release, fabrication, and characterization. In biomedical science, drug delivery system (PDS) are becoming increasingly relevant due to their advantage over traditional methods. Polymeric nanofibers have demonstrated promising properties for the development of these systems. In this work, we propose the fabrication of structured nanofibers loaded with a drug using the electrospinning technique for topical administration. And the electrospun nanofibers were obtained from PLA and PBAT polymers in a 45 to 55 weight ratio. Before electrospinning, curcumin was incorporated into the polymer solution at 10% by weight. Curcumin, a compound with anti-inflammatory properties, can be used as a complementary treatment for conditions such as arthritis and skin disorders. The presence of curcumin within the nanofibers was confirmed by Fourier-transform infrared and UV-vis spectroscopy. Scanning electron microscopy image revealed fibers with homogeneous morphology and an average diameter for 148 nanometers, and UV-vis analysis indicated that approximately 75% of the incorporated curcumin is available for release. So Electrospun PLA PBAT curcumin nanofibers are expected to serve as effective drug delivery carriers. As shown in figure, the electrospinning setup consists mainly of a polymer solution contained in a syringe fitted with a metallic needle and a high voltage power supply connected to the needle and a metallic collector. When a voltage in the kilovolt range is applied, the polymer solution delivered at a controlled flow rate by a syringe pump forms droplets and the needle tip. Due to the electrostatic field between the needle and the collector, these droplets become polarized, forming what is known as a Taylor cone. At this point, the surface tension of the solution is balanced by the electrostatic forces. When the electrostatic force exceeds these surface tensions, the solution is drawn toward the collector, stretching and thinning into fibers on this way. Mineral dissolvents evaporate, leaving behind solid polymeric fibers on the collector. In this table, I present the experimental parameters. So the electrospinning condition was voltage 15 kilovolts, needle to collector distance 10 centimeters, flow rate 0.03 milliliters per hour, and needle 18 weight. It's important that the fibers were collected on a copper collector wrapped in aluminum foil. Scanning electron microscopy analysis confirmed nanometric fibers with an average diameter of 143 nanometers. These fibers exhibited a uniform morphology without bead formation, and this is important. Figure 2 compares fibers from the polymer blend along with those containing curcumin, showing a notable reduction in a diameter with curcumin incorporation. The Fourier-transform infrared spectra revealed functional groups of the polymer blend and curcumin, confirmed their presence without chemical interaction. And the UV-vis spectroscopy confirmed curcumin incorporation and quantified its release capability. If you want more details of this part, You can write me in the chat application. In conclusions, polymeric nanofibers incorporating curcumin were successfully fabricated with an average diameter of 143 nanometers, homogeneous morphology, and no beads formation. About 75% of the curcumin were retained and available for release. These nanofibers are expected to function as efficient drug delivery systems. In the future work will include drug release studies and propose optimization to enhance drug loading capability. Finally, I would like to thank the Secretary of Science, Technology and Humanities, as well as the Secretary of Research and Graduate Studies for partially funding this project, and the Physics Department at CIMRSTAF and the Matea Group for their support in the instrumental analysis. Thank you everybody for your attention.